All right, so the first lesson in Unit 3 is energy changes. And this entire unit, we will have to deal with energy change, heat, and rate of reactions. So this lesson will first talk about the difference between kinetic and potential energy, and then we'll talk about thermal energy, so a lot of definitions, heat and temperature, and then we'll talk about the different kinds of chemical systems. After, we'll learn about endo versus exothermic reactions, which are extremely important for chemistry. And then lastly, a little bit on nuclear reactions. All right, so the first word that we're going to learn is thermochemistry. Thermo in English means heat. All right, this means we study the energy changes that comes with a physical or chemical change. This part of the course is called thermodynamics. It's the study of heat, essentially. But we have to be careful because the word heat is used very loosely in common language. It has a specific meaning in science. And same as the word energy. Okay, we use the word energy very loosely in common language, but in science, energy is simply the ability to do work. And the unit of energy is joules. So what do you mean by work? Are you working now? You're looking at a computer screen, you're trying to learn some chemistry. Is that work? Work also has a very specific definition in science. Work is the amount of energy transferred to an object by a force that causes the object to move. So in order to have work, there must be a force that causes something to have a displacement. There must be a certain distance that the thing moved. If you're pushing against a wall and the wall doesn't budge, you're not doing work. Okay, you're using a lot of force, but no work is done because there's no displacement. An example of work will be a rocket lift off. The fuel is being burned and it produces a lot of energy, and this thrusts the rocket upwards with the displacement, so that is work being done. Another example is car traveling on the highway. The energy is derived from burning fuel again, which converts into kinetic energy, which moves the car forward, doing work. Other examples of work including a cat jumping on a table or you walking, anything that involves movement. Now, there are different kinds of categories for energies, and all energies can be classified as either kinetic or potential energy. Kinetic energy is relatively easy to understand. It's the energy of motion. Kinetic means to move. Anything that is moving will carry with it kinetic energy. For example, a falling object. If you throw something out the window on a 20-story building, that thing will start to fall and it will pick up speed as it falls and it will increase in kinetic energy. If you get hit in the face by a baseball, it's going to hurt. How much it hurts and how much damage it can do depends on how fast the baseball is flying. If it's thrown by a regular person, you might have a bruise. If it's launched from, I don't know, like a launcher, then you might die because that baseball will have a lot higher kinetic energy. So the faster that something moves, the higher the energy and the more damage it will do. The other type of energy is potential energy, and this is the energy derived from something's position or its composition. In chemistry, we'll focus more about the composition. So there is chemical potential energy in the subgroup of potential energies. We will consider energy stored inside of compounds. If you think of an apple, you can eat that apple and you will then digest that apple and convert that into energy that your body can use. And then you will use that energy to do whatever you need to do. How does that work? Well, because apples or any other food that you eat contains chemical bonds. Okay, and those chemical bonds are held together with energy. If you have two atoms beside each other. The electrons of one atom will attract the nucleus of the other atom, and this attraction keeps them together. And this is a form of potential energy. And in order to break those bonds, you need to input energy to pull them apart. Right? So energy is stored within chemical bonds. So thus, you can convert chemical bonds by breaking the bonds into energy. All right, and the second type of energy will be gravitational potential energy. This is the one that physics normally focuses on. Imagine the same apple being placed on a table, and that table is a certain distance from the floor. The apple will have a certain amount of gravitational potential energy because it has the potential to fall to the floor. Right, so these are the two types of potential energies. We'll primarily be looking at the chemical potential energy.
Mr. Joe, I was just waiting in the waiting room.
Oh, okay. Yeah.
Also, I had a question.
All right, so there's another way of thinking of kinetic versus potential energy. So imagine a hammer. You're about to strike a nail, but you're holding the hammer in your hand, so the hammer is not moving. This would give the hammer potential energy, right? The energy of its position. From that height, when you drop the hammer on the nail, it's going to do work, but it's not doing anything yet, so that's potential energy. As you swing the hammer, it picks up speed, and this will increase its kinetic energy. And as it hits the hammer, hits the nail, it causes the nail to go into the plank. Well, that's mechanical energy, okay? And in the lower picture, you're shooting an arrow from a bow. When you draw the bow, you store potential energy in the bow. You bend the bow, and that shape has a lot of potential energy. The moment you release the bow, you release that potential energy, and that will be converted into kinetic energy of the arrow, which shoots the arrow. All right, so please know the difference between potential and kinetic energy. Now, thermal energy is the total amount of potential energy and the kinetic energy of a substance. Okay, thermal energy is the sum of potential plus kinetic. Okay, so the quantity of thermal energy, how much of this you have, it depends on how fast the entities are moving in the substance. Okay, so thermal in English means heat, and how fast things move is exactly what temperature is. So if you consider the barbecue grill, when a substance absorbs thermal energy, it heats up. If something releases thermal energy to the surrounding, then itself will move more slowly, cooling down. All right, so if you look at the barbecue grill, in this situation, the potential energy in the fuel, you're burning the fuel, you will convert into thermal energy, which heats up the barbecue, which transfers the thermal energy into the barbecue. Okay, so to recap, thermal energy is the sum of kinetic and potential. If you increase the kinetic energy, you increase the thermal energy because it's part of thermal energy. Okay, which brings us to heat. What is heat? Well, heat is the transfer of thermal energy from warm object to cool objects. Okay, heat is a transfer of energy. If you're not transferring the energy, that is not heat. Right? In English, we use heat to describe something hot, something warm. In fact, heat is the transfer of energy. You have to be a little bit more precise with the definition. Temperature is the measurement of average kinetic energy in a substance. Okay, so if you look at the boxes, on the left, you have a box at 10 degrees Celsius, and the little particles in there, they're kind of moving around. Everything moves randomly. However, if you heat that up to 39 degrees Celsius, as temperature increases, their kinetic energy increases, the particles all move faster. Okay, so that's the definition of temperature, the average kinetic energy of the entities in a substance. Okay, so these definitions, please make sure that you guys are familiar with. They're similar, but they're not the same. Now, here's a pretty interesting question. A cup of hot coffee versus an iceberg or a glacier. Which one has higher temperature? Guys?
Coffee?
Yeah, it's quite obvious. The coffee would have higher temperature, right? It's hotter. So the coffee feels hotter because of the higher average kinetic energy and thus higher temperature, which makes total sense. Now, which one has greater thermal energy? See, that's a harder question. Which one is it, the coffee or the iceberg? No one wants to guess?
Is it? I think it's coffee. And like,
Why do you say coffee?
because I feel like the. Oh, wait. No, wait. I think then it's iceberg. No, because I mistaken it with the temperature. I was going to say the particles move faster, but.
It is true that the coffee has faster particles.
Yeah. I don't know.
No, you're on the right track. And then you stopped yourself, but wait, that means you're thinking. Thermal energy is not the same as temperature. The higher the temperature, the higher the thermal energy, yes, but thermal energy is the sum of kinetic and potential. Right? While the coffee has higher kinetic energy for being hotter, the iceberg has way more water molecules than a cup of coffee. And each molecule of water has 2 bonds with hydrogen from an oxygen, and those all contain potential energy. So an iceberg being cold, but it has way more mass, so there's way higher potential energy than the coffee. So the thermal energy, the sum of both kinetic and potential, will favor the iceberg. So the iceberg will have higher thermal energy for having way more particles than the coffee. The temperature is irrelevant because, you have way more particles. It kind of outmatches the difference in temperature. Does that make sense? So if you want to consider thermal energy, you need to consider both kinetic and potential. And if there's a huge difference in iceberg compared to a cup of coffee, then you just look at the potential energy from the excess particles. Okay, so please make sure you know the difference between thermal energy and temperature. All right, so you may have heard of this at some point in your life, in a previous course maybe. The law of conservation of energy. It simply says energy cannot be created or destroyed. If you have energy, you're going to have energy forever. Okay, you can convert that energy into another form, and you might not be able to use that new form, but it's still there. Okay. In other words, the total amount of energy before and after a chemical reaction should stay the same. You are not going to create energy from nothing. You're not going to just destroy energy into nothing. All right. And if you're studying the chemical world, you're not going to study the entire universe. You're going to be focused on something that you're interested in. Maybe a reaction in a flask. That's what we call a chemical system. Surrounding. If that content in that flask is your system, then the lab bench behind you is the surrounding. The person next to you is the surrounding. The flask itself is the surrounding. right? And if you just combine the system and the surrounding, you have the entire universe. Does that make sense? We need to distinguish between the system and its surrounding. When we talk about the system, we talk about the chemical reaction being studied. The surrounding is everything outside of that. And when it comes to systems, there are 3 different kinds of systems. You can have an open system, a closed system, or an isolated system. They're not exactly the same. An open system is a system in which both matter and energy are free to enter or leave the system. All right, so for example, your house is an open system. Even if you close the doors, I'm pretty sure there are holes in your house somewhere. Right? Little bugs can still come in and go out. You might have a crack in your window. You might have a crack in the wall. You might have a chimney. Unless you patch them all up, you have a completely closed space, you eventually suffocate to death because you have no ventilation. Only then would you have a closed system. All right? If you seal a box very tightly, inside of that box you have a closed system. Matter cannot enter or exit the box, but energy can. And you're not going to stop heat and energy from entering and leaving the box. So a closed system blocks matter but does not block energy. Does that make sense? An isolated system is a system that blocks both energy and matter. Matter can go in or out, but then neither can energy. Okay? We actually don't have any isolated systems on Earth or in this universe for that matter. Isolated systems do not exist, well, except for one instance. There's only one example of an isolated system that we know. Do you know what that is? Can anyone venture a guess? What is the only known isolated system that we know of?
Space?
Space? Well, which part in space?
A black hole.
Oh, okay. A black hole. That's arguable. A black hole, you learn that only things could go in. You're never coming out. That is mostly true. But then, Stephen Hawking discovered Hawking radiation, so things do come out of the black hole. So not entirely an isolated system, but for a lot of intents and purposes, yeah, pretty much. Anything aside from a black hole.
Like for example, if we pull out the air in some place, like in a box, and put something in there, like will that still be considered an isolated system if there is like nothing else?
No. If you suck out the air in a box and you put something in the box, well, obviously that thing can't get out of the box, right?
Yeah.
But energy can.
Oh, true. Right.
If there's a nuclear war outside, I'm pretty sure the content of that box would have some kind of, will be affected somehow. The temperature will probably increase by a little bit. That wouldn't be an isolated system. Somebody said space.
Yeah.
You might want to expand on that idea. What do you mean by space, right? Which part of space? Because the sun is in space, the Earth is in space.
Like, I don't know, like I was talking about the space in general. I didn't really think about it that
way. Space in general, okay. It's called the universe.
Oh, universe, yeah.
That's what you meant, right? Okay. That's the correct answer.
Yeah.
The entire universe is the only isolated system that we are absolutely sure of. Nothing can leave the universe. It's not even energy, and nothing is coming into the universe from outside of the universe. Okay? This is an isolated system. We're not even sure whether there is an outside of the universe. We proposed the multiverse, but I mean, we have no way of testing that. There's no way for us to detect something not in our universe. By definition, all of our scientific experiments happen inside the universe, so that's preposterous. It's like saying that we have an invisible pink unicorn in the room, and there's no way for us to detect that unicorn with any of our senses. I mean, you could believe that there is an invisible pink unicorn, but that doesn't really change anything. You might as well say it doesn't exist because for all intents and purposes, it doesn't exist. So the outside of the universe is kind of like that. We can't know whether that exists because we are by definition trapped in our own universe. So for us, the universe is isolated. That is the only isolated system. You can't have any other isolated system. You can try your best to build an isolated system on Earth, right? But our equipment cannot stop heat and energy from entering and exiting. You can slow it down. You can make it very energy efficient so that the heat doesn't escape, but some will always escape. All right, so that's the difference between the three chemical systems. Okay, so in order for chemical reactions to occur, we must first break bonds and then make new ones. That's the definition of chemical reactions. If you want to break bonds, you must input energy. All right, because you need to separate the atoms away from each other. And if you do that, you better pull them apart with energy. Otherwise, they're going to be stuck in a covalent bond. So if you input the energy to separate the atom because they're attracted to each other electromagnetically, if you separate them enough, then congratulations, you broke the bond. That requires energy though. Now, when you form a bond, the opposite occurs. You release energy. Why? Because in the universe, matter always want to go to their lowest energy state. All right? Two separate atoms. Individually, they have relatively high energy because they want a full, stable octet. So that's why they make chemical bonds. If they do that, they drop to a lower energy level. I don't mean the same energy level as in the one we learned in orbitals. I mean, they drop to a lower energy state as a whole, and that's more stable. Okay, so the atoms bond with each other because their products typically have lower energy than their individual atoms. So that's why making a chemical bond releases energy, because less energy is required to maintain that bond than to maintain individual atoms. So if you consider the combustion of methane in the picture, in order to have this reaction, you must break all of the bonds in red. The carbon-hydrogen bonds must be broken. The oxygen-oxygen bonds must be broken. If you break these bonds, then you're ready to make new ones. You see what I mean? So first you got to break the bonds, and to break those bonds, you need to input some energy. All right, so you do that. And then you rearrange the atoms, you make carbon dioxide and water, you make the new bonds in blue, and they will give you energy. So here's the question. Do you have a net gain or a net loss of energy? Okay, what do you think? Using common sense, you're burning methane.
Gain. I mean, a loss.
Loss, yeah, that's a better answer. Okay, it depends on the perspective, really. From the perspective of methane, you lose energy. Right? That's the whole point of burning methane. We burn natural gas so that it releases energy. We can use that to heat our homes, right? Meaning that this is a net loss of energy for the reaction, right? What does that mean in terms of the bond energies? It means it takes less energy to break those red bonds than the energy produced from making the blue bonds. You see what I mean? It's like a business. You want to start a business. You want to sell chocolate bars, for example. Well, you need to invest some money. You got to buy the chocolate bars from somebody. And so you buy chocolate bars for $1 each. And then you go ahead and sell those chocolate bars for $2 each. So you have to first spend some money, and you make some money, and you make more than you spend, you turn a profit. Congratulations. But not all chemical reactions turn a profit. This is an example where the products actually release more energy than the reactants use. So this is called exothermic. So there's exothermic versus endothermic. Exothermic, exo, exit, means to leave. Exothermic means heat leaving. An exothermic reaction releases energy into the surrounding. right? So the system itself would have lower energy at the end. So this is burning methane. You break the bonds, you consume some energy to break the bond, but the new bonds that you make releases a lot more energy than that. So you have a net loss of energy. So the products have lower energy than the reactants. Energy is released. Okay, if you release energy with the reaction as exothermic. The opposite, endothermic, endo means inside. The chemical reaction system will absorb energy from the surrounding. As a result, you gain energy as a system, so your products have more energy than the reactants. Right? And meaning that you use more energy to break your bond than the energy you release from breaking or from forming the bonds. So you consumed more energy than you released, you gain energy as a whole. So you buy chocolate bars for $10 a piece, you sell them for $1. That's a quick way of losing money. And so that would be an endothermic reaction. The products have higher energy than the reactant, energy is absorbed. Does that make sense, guys? So you have to know the difference between exothermic versus endothermic. So let's test that knowledge. For each of the following, identify whether it is exo or endo. So just as a group. A, water evaporates into steam, exo or endo?
Endo?
Anyone disagrees? No? Right, that's endo. Okay, if water evaporates into steam, water needs to absorb energy from the environment in order for this to happen. Okay, liquid water is held together tightly via hydrogen bonding. If you want to evaporate the water and just separate them into the gas state, you got to pull them apart, which requires energy, which you need to suck from the environment. That's why you need to apply heat in order to evaporate water, endothermic. What about candle burning?
Exothermic?
Exo?
That would be exo, right? A candle burning generates light and heat. You put your hand near the flame, it's warm because the heat is being produced from this burning reaction of candle and wax. Whatever wax is being turned into, that has lower energy than the wax itself. And that difference in energy is released as heat. That's why it feels warm near a candle. What about combustion of gasoline in a car?
Exothermic?
Yeah, for the same reason that burning candle is exothermic, you burn gasoline, same story. You generate energy. That's the whole point of burning gasoline, so that the energy of this reaction, the product form, carbon dioxide and water, they have lower energy than gasoline itself. The difference in their energy is released as, well, partly released as heat, and then we convert that into kinetic energy of the car, which is then used to move the car, okay? Melting of ice.
Endo?
That's endo. For the same reason that water evaporating into steam is endo. If it snows outside, you may have noticed that the snowy day is not that cold. But the day that follows, where it's not snowing, but there's now snow everywhere, that's going to be a cold day. Because a lot of heat in the atmosphere is being used by the snow in order to melt into water. Right? So you have a cooling effect on the environment. So melting ice and melting snow absorbs heat, which means it's endothermic. So splitting of nitrogen into individual atoms.
I'm not sure, but I think it's exothermic.
Exo.
I don't know.
Be careful what this is saying. Nitrogen is into, you break them into two ends. You break that triple bond between the two nitrogens. And we just said, endo, if you want to break bonds, you need to input energy. Making bonds releases energy, but you break in the bond, you just have a net loss of energy from the environment and a net gain of energy in the system. You need energy to break the bonds, endothermic. Okay, so breaking bonds is endothermic. Last one, dissolving barium hydroxide in water, and you observe a temperature decrease in the surrounding. Endo or exo? The key word is temperature decrease.
Endo?
That's correct, endo. Same reason as melting of ice. If you decrease the temperature of your surrounding, well, where did that energy go? It's used to do your reaction, right? So if you want to dissolve barium hydroxide in water, you need energy from the environment to help you break the bonds of barium hydroxide so that water can then surround them. And the water will become colder. Okay, so endothermic reactions will cool your surrounding, whereas exothermic reactions will heat up your surrounding, like burning candles. Now, please make sure that you know which is which, endo versus exo, and don't misremember them. I remember I taught this to some grade 11 students at another school. They had a BC curriculum, not an Ontario curriculum, so you learn this in grade 11. And I gave them a quiz. And it was pretty simple. It's like a true and false question, except I asked endo or exo. You have a 50% chance of getting this correct. It's one or the other, right? So I had like a good 6 to 8 questions, I can't remember, of endo versus exo. So this student magically got 0 for that question. Okay, I remember he didn't leave any blanks. He attempted all of the questions. It's just that he got all of them wrong. I refuse to believe that this was luck. I want to believe that he just got those mixed up. He remembered endo as exo, exo as endo, and he did all of those questions correct. It's just he misremembered which is which. But then I realized this kid is getting 6% in my class right now. So I don't think he studied to get there. So I'm pretty sure he guessed all of them and just guessed all of them wrong. You have a 50% chance of getting them right. If you do the probability, that is a really impressive feat. I've never seen an actual 0 on a quiz, because if you just scribble down anything, chances are somewhere on the test you're going to get some marks. But yeah, that kid really opened my eyes there. My point is, don't misremember which is which. Remember that exo releases heat, endo absorbs heat, and you should be fine. Okay. The last little bit of this lesson is about nuclear energy. So far, we've talked about physical change and chemical change, but nuclear change also releases energy. And there's 2 types of nuclear reactions. The first one we're going to look at is nuclear fusion. And fusion means to come together. Nuclear fusion refers to the combination of 2 or more nuclei of relatively low mass to form a heavier, more stable nucleus. And a prime example of this happening is in the sun. Not just the sun, but all stars in general. That's the definition of a star. You must be able to do nuclear fusion. Jupiter is not a star because Jupiter is not massive enough for the gravity to crush the hydrogens to fuse that into helium. If Jupiter is able to do that, then it will become a star, but alas, it can't. Jupiter needs to get a lot bigger in order to do that, but the sun can. Inside the sun, hydrogen, specifically deuterium, hydrogen-2, and hydrogen-3, tritium, they are being smashed together into helium-4. And helium is very stable. And if you count the mass, well, you have 1 neutron left over, and that neutron is released along with energy. Okay? Mass is being converted into energy in the sun. And that's why the sun releases a crap ton of energy, because E equals to mc squared. And with that equation, you have to multiply mass by c squared, the speed of light squared, which is a huge number. So the sun releases an unbelievable amount of energy via nuclear fusion. We don't know how to do that. Okay, we are trying to learn how to do nuclear fusion on Earth so that we can harness the energy of the sun on Earth by basically making a new mini sun. Except we don't want to make a new mini sun because we have another problem. You just destroy the city that you're in. If you manage to make a tiny sun in the lab, you can say goodbye to like a 500-kilometer radius. Okay, goodbye country. We're trying to figure out cold fusion. We fuse atoms together to make energy, but then, not make it hot so that it will melt the city. We don't know how to do that. If you can manage to do that, we'll be seeing your name in the textbooks. If one of you actually goes into that field and discovers cold fusion, in your Nobel Prize acceptance speech, I'll mention that I was your teacher. I would really appreciate that. But yeah, this is the frontier of science. That will be one of the greatest discoveries of the 21st century. If you can manage to achieve cold fusion, then you will solve the energy crisis. We no longer have to burn fossil fuels, just do fusion. And this is quite safe. You can manage to do it the way that I described. So everybody will get a ton of energy. Imagine how much energy the sun produces. If we can do that on Earth, everybody gets internet, everybody gets Wi-Fi, everybody's happy. But alas, we can't do that. What we can do is nuclear fission. The opposite of fusion. Fission means to break up. We could take a large nucleus, smash something into it so that it breaks into two smaller nuclei. All right, and this process will generate energy as well via E equals to mc squared. And we can do this if you take a large enough nucleus that is unstable. All elements above number 83 are unstable because we have too many neutrons. It just doesn't hold together well. All you have to do is poke it a little bit with something. It will decay. It will naturally decay, but that decay is too slow. We want to speed it up, right? So that's how we discovered that we can break up an atom. Atom means indivisible in Greek. Well, that no longer has any meaning. We can divide the atom. And as a result, generates a tremendous amount of energy. We can either harness that energy for a productive purpose, a constructive use like nuclear energy, or it can have destructive applications like a bomb. Uranium is a very valuable mineral, to say the least. We can mine uranium from the Earth, enrich that uranium. The uranium-235 nucleus is very useful to us because we can shoot a neutron at it. It will make it so unstable, it will split up into krypton and barium along with 3 other neutrons. And this splitting generates energy. And if you just look at the math here, 1 neutron hits 1 uranium atom, you make 3 other neutrons. And guess what? Those 3 other neutrons will find 3 other uranium atoms, split those, and each of those will have 3 neutrons for a total of 9 neutrons. And then those 9 neutrons will find 9 other uranium atoms, makes 27, and then makes 81. And you see where I'm going with that. It's exponential. All right, you can have an exponential growth of how many atoms are split up. And you learn exponential growth, this curve goes up really steeply. And this quickly turns into an uncontrolled chain reaction, which results in an uncontrolled explosion. Okay, that's the science behind an atomic bomb, the uranium bomb. You start just with 1 neutron, it grows exponentially, you can blow up an entire city with that amount of energy. Now, we're probably not interested in blowing up cities anymore. So we can do this in a nuclear reactor. In fact, in Pickering right now, they're doing that. Okay, Ontario has mostly hydro and then some nuclear energy. Okay, we rarely use the other sources because it's unclean. But nuclear energy accounts for 15% of electric energy in Canada, and that is achieved via fission of uranium. In a power plant, they do the same reaction, but they don't allow the explosion to happen. They do that in a controlled manner, step by step, so that each stage you harness that energy, you heat up some water into steam, and then this steam will then be used to turn a magnet in a coil and that generates electric current. Right? This is highly efficient compared to burning fossil fuels. For the same mass of uranium versus coal or methane, you generate 26 million times more energy with nuclear reaction. So this is very, very reliable. Nuclear power is extremely good. Like all the other forms of generating electricity that doesn't produce greenhouse gas suck. Right? They suck with their own special way. But nuclear energy is actually reliable. It can generate a lot of energy with just a small amount of reactant. It does have problems, namely Chernobyl. If something were to happen in Pickering, yeah, we might have like a meltdown, and we are pretty close to Pickering. You might have to move, but we don't have an accident, and I don't think an accident is going to come up anytime soon. But there's always that risk, right? So some people are concerned about that aspect of nuclear power, and it generates a lot of radioactive waste that will be radioactive for tens of thousands of years. We just bury them underground into like thick meters of concrete and hope for the best. And hopefully there's no crack, like no little microorganisms start to just crack up the rocks. That's what we have right now. Okay, nuclear energy, it is highly efficient. It generates a lot of electricity with just very little materials. A lot of countries are looking into nuclear energy. Not every country has nuclear. Canada is one of the few that does. So if you want to compare the three different changes, keep in mind these are not to scale. There is a phase change, a physical change. Water vapor condenses into liquid water. Now that releases a tiny bit of energy, 44 kilojoules per mole. That is quite small for 1 mole of water, just 44 kilojoules. You don't really do much with that. A chemical change involves a chemical reaction. For example, if you burn hydrogen with oxygen, you will produce water. And for every 1 mole of that, you have 285.8 kilojoules of energy, which is a lot higher than 44. So a chemical change will produce more energy than a physical change. But check out nuclear. If you fuse hydrogen into helium, you will generate, get this, 1.7 times 10 to the 9 kilojoules per 1 mole of substance. That is 1.7 billion kilojoules. That is not in the same stratosphere as the other two. So nuclear energy is tremendously efficient. If we can manage to harness that, then we're good. All right, but no, we can only do that very inefficiently in a fission plant. So basically, this concludes our lesson here. We learned about what energy is, ability to do work. We distinguish between potential and kinetic energy. We defined what thermal energy is, just a sum of kinetic plus potential. We know what heat is, transfer of thermal. Temperature is the average kinetic energy, and we learned the conservation of energy. You can't create or destroy energy, but you can convert one form into another. Like right now, you're converting electric energy into light energy with the computer screen. Electricity is being used to project whatever that you're looking at. We learned